Beneath the calm smoothness of the night sky, a silent sentinel named Tess orbits our Earth, gazing out into the far reaches of space. It's entrusted with a profound and pioneering mission. It seeks out the shadows cast by worlds far beyond our planet, worlds orbiting stars quite unlike our Sun. Among the countless observed stars, one in particular has caught Tess's eye, a red dwarf known as TOI 715, holding in its grasp two planets, each potentially home to life beyond our system. So, among the latest discoveries, we have two entire rocky terrestrial planets. One of them has already confirmed its existence. Its companion, in turn, is still a candidate awaiting the final verdict of further observations. So how did a satellite no bigger than a small bus orbiting our planet become the key to unlocking the mysteries of planetary systems many light years away? And what would it take to detect the existence of such distant worlds from our vantage point millions of miles away? Launched in 2018 to the vast silence of space, Tess, the transiting exoplanet survey satellite, has been sent on a monumental journey. A mission designed with the sole purpose of unlocking the secrets of distant worlds orbiting stars far beyond our system. Armed with an array of sophisticated instruments, Tess stands on its watch, watching some of the cosmos unceasingly. Tess's innovative design combines the latest in space technology at the time and includes an array of wide-angle cameras that provide an unprecedented panoramic view of the sky. This array is carefully calibrated to detect minute changes in starlight brightness, a sure sign of a planet passing in front of a host star. This precision allowed Tess to survey more than 200,000 stars during its 2-year primary mission, with each observation having the potential to be the key to discovering a new world. However, Tess does not drive its narrative alone, but alongside Kepler, its predecessor in the search for exoplanets. Although Kepler's eye was fixed on a smaller field of stars, his explorations were also fruitful, discovering thousands of new worlds and painting a picture of a galaxy teeming with planets. Tess builds on this legacy, casting a wider net as part of its all-sky survey and bringing us closer to the dream of finding another Earth. Together, Tess and Kepler have transformed our understanding of the cosmos, turning a once fanciful version of countless worlds into a vivid reality. The telescope's planned 2-year primary mission has been extended, illuminating our path toward the quest to understand our place in the universe to this day. The observatory's monumental work has discovered more than 7,000 candidate exoplanets as of earlier this year. This remarkable achievement only emphasizes the vast number of planets outside our solar system. The work of compiling a catalog of these celestial bodies is no small task. It begins with meticulous observation of the stars in search of characteristic features of companion planets. The criteria by which an object is considered a candidate exoplanet are very strict. They require clear evidence of consistent orbital patterns, an estimate of size and mass that suggests the presence of a solid or gaseous body, and most importantly, the possibility of the planet being in the habitable zone of its star. At the heart of our search for Earth-like worlds is the concept of the habitable zone, often called the Goldilocks zone. This is a notional band around a star where conditions may be optimal, neither too hot nor too cold, for liquid water to exist on the surface of a planet, an essential ingredient for life as we know it. Historically, the giants of space, massive planets with dense gaseous atmospheres, have dominated our catalog of discoveries. Their size and proximity to their host stars make them more visible to our observational instruments, casting long shadows and causing more pronounced wobbles in starlight. The most important area of exoplanet research, however, is the detection of small Earth-like planets. These rocky worlds, similar to our Earth, present a more difficult challenge. Their subtle signal is often lost in starbursts. In an effort to detect a myriad of such worlds, astronomers have owned a considerable number of methods to do so, from astrometry to gravitational microlensing. About 50 planets have been discovered using pulsars. However, we won't focus on each of those today. That's a topic for a different video. But let's start with the basics to make sure we're all on the same page and briefly go over a trio of sophisticated methods, each as good as the other. These methods, direct imaging, the radial velocity method, and the transit method, form the backbone of our celestial search. Direct imaging captures the elusive photons that emanate from planets billions of kilometers away. To date, more than 230 confirmed exoplanets have been discovered using this method. This method, somewhat similar to photography, is most effective for large planets at a considerable distance from their stars, where the star's glare does not block the planet's faint light. Next, we dive into the radial velocity field, a method that allows us to read the celestial interaction between stars and their planetary companions. As planets orbit, they exert a gravitational pull, causing their stars to wobble slightly. This wobble affects the color of starlight, shifting it to the red or blue part of the spectrum. It was through careful measurement of this phenomenon that the presence of more than 1,000 confirmed planets was inferred. However, it's the transit method that's revolutionized our cosmic census, especially with missions such as Tess and Kepler. This method allows us to observe the periodic dimming of a star when a planet transits in front of it, blocking out some of its light for a moment. The depth of this dimming allows us to determine the size of the planet and the regularity of the transit, its orbital period. Tess and Kepler used the power of the transit method to incredible effect, scrutinizing thousands of stars in search of signs of planetary transits. With Tess's wide-angle cameras scanning large areas of the sky and Kepler's precise focus on a fixed field of stars, these observatories have cataloged countless new worlds. The elegance of the transit method lies in its simplicity and the wealth of information it provides, from planet sizes and orbits to potential atmospheres when combined with other methods. The discovery of Earth-like planets located in habitable zones of their stars is a difficult task, akin to watching a firefly hovering near a lighthouse from a few miles away. These terrestrial worlds, smaller and dimmer, often remain obscured by the glare of their much brighter stars, making their detection an unusually delicate and precise task. The difficulty lies in the enormous size and brightness mismatch between an Earth-sized planet and its host star. When such a planet passes in front of its star, it blocks only a minuscule fraction of the star's light, resulting in a dip in brightness so slight that it tests the limits of our most advanced observational technology. However, in the search for these elusive worlds, M-type dwarf stars are becoming beacons of hope. These stars, smaller and cooler than our Sun, offer a unique set of advantages for detecting Earth-like exoplanets. The reduced luminosity and size of M-dwarfs means that planets orbiting them can produce some pronounced transits, making their detection more feasible. In addition, the habitable zone around these stars is much closer than around stars such as our Sun, resulting in shorter orbital periods for habitable planets. This proximity not only leads to more frequent transits, but also increases the chances of capturing these events, thereby increasing the likelihood of detecting potentially habitable worlds. Well, let's in fact move on to the recent discovery of Dransfield and her team, and that caused a lot of interest in the astronomy community. As a result of their painstaking search, they discovered not one, but two terrestrial planets orbiting a red dwarf called TOI 715. Now, TOI 715b is the first of these two planets. It's been confirmed, and its existence is already on Discovery list. This world, which has a radius 1.5 times that of Earth, revolves around its star every 19 days and has an equilibrium temperature of 234 Kelvin or minus 38 Fahrenheit. It's a cold realm, but at the same time a very potentially habitable place if it has an atmosphere capable of trapping heat. TOI 715b's journey from mere candidate to confirmed exoplanet began with the Tess transit method. It detected the slightest attenuation of the host star's light as the planet passed in front of it. This initial detection was backed up by a series of follow-up observations involving ground-based photometry, high-resolution imaging, and statistical validation using facilities like the Las Cumbres Observatory Global Telescope Network and the Extra facility. Its companion, labeled with a more convoluted name, remains only a candidate. We're awaiting a clarifying glimpse of further observations. If confirmed, it would be the smallest exoplanet detected by Tess in the habitable zone. The estimated temperature of this planet is 215 Kelvin, equivalent to a very chilly minus 72 Fahrenheit. It's only 6% the size of our Earth and makes a complete revolution every 25 days. This orbital period suggests that it's just inside the outer boundary of the habitable zone. The 4:3 commensurability of the orbital period with TOI 715b gives the system interesting dynamics, potentially indicating orbital resonances. Such resonances are known to affect the long-term stability and evolution of planetary orbits. In resonance systems, gravitational interactions can lead to changes in eccentricities and inclinations of orbits over time, potentially stabilizing orbits by preventing close encounters. The study suggests that confirming a companion candidate and its commensurate orbit can provide valuable insights into the mass and dynamical state of the system, allowing for detailed characterization through dynamical systems into the future. Tidal forces play a crucial role in shaping the orbits and rotational states of planets in resonance systems. These forces can lead to tidal heating, affecting the geologic activity and heat distribution of planets, which in turn can affect their habitability. Understanding these dynamics is critical to accessing the long-term stability and habitability of planets. As we've said, the search for habitable worlds goes far beyond simply finding a planet in the habitable zone. Planet's atmosphere, composition, and geologic activity play key roles in determining its habitability. For example, a dense atmosphere can trap heat, expanding the habitable zone, while a thin atmosphere can do the opposite. However, the enigmatic nature of planets orbiting M-dwarf stars with their unstable flares and radiative emissions presents a paradox in the search for habitability. These stars, with their frequent stellar activity, have the potential to strip the atmospheres of those very planets. The authors of the study note that while starbursts can provide the energy needed to catalyze biological processes, they can also pose a significant threat by contributing to the loss of atmospheres or damaging existing biological structures, depending on the composition of the atmosphere and the presence of protective magnetic fields. But it is in such a turbulent environment that the James Webb Space Telescope stands at the ready to use its advanced suite of instruments and shed light on the composition of planetary atmospheres. JWST uses the technique of transmission spectroscopy, capturing the faint signals of starlight passing through planetary atmospheres. This method allows us to relatively accurately decipher the atmospheric constituents from water vapor to methane, each leaving a unique spectral fingerprint. While in orbit, Webb has a very busy schedule of planned observations. But on Earth, our team of scientists is also wasting no time and has already calculated the transmission spectroscopy metric, or TSM for short, for these planets. TSM plays a crucial role in assessing the prospect of exoplanets for studying atmospheres using transmission spectroscopy. Developed by Kempton and his team in 2018, TSM is a standardized measure for comparing the potential of different exoplanets to reveal the characteristics of their atmospheres using this method. For TOI 715b, TSM calculations were made under different assumptions about the planet's composition, both rocky world and water world. These calculations take into account the size of the planet, which is slightly larger than the threshold commonly used to define terrestrial planets. As a result, different scaling factors have been applied to ensure a fair comparison with other known exoplanets. The results show that the planet, especially in the water world scenario, may exhibit a transmission signal similar to the well-studied mini-Neptune LHS 1140b in the constellation Cetus, assuming the presence of detectable atmospheric features. However, in the rocky scenario, the TSM of TOI 715b is below the threshold recommended for terrestrial plant observations, suggesting that more than one JWST transit may be required to detect meaningful atmospheric features. The authors of the study suggest that molecules such as water, vapor, and carbon dioxide play an important role in maintaining surface temperatures suitable for the existence of liquid water. The presence of an atmosphere with these greenhouse gases could expand the habitable zone and increase the chances of life. The position of planets in the conservative habitable zone, as well as their potential rocky composition, naturally raises questions about their habitability and the early processes that could lead from inorganic compounds to the precursor molecules of life. In the meantime, we look forward to JWST finally setting its eyes on this system, not only because of the scientific debate they will generate about the habitability of planets orbiting M-dwarfs and the effects of stellar radiation on them, but also because of the perspective they promise. A perspective that promises not just answers, but perhaps a new understanding of the very nature of habitability in the universe. For decades, all of humanity has been asking one of the most important questions for the entire universe. Are we alone? Today we will challenge the Fermi paradox by finally getting closer to the most anticipated answer with the help of artificial intelligence. Through millions of images and hundreds of hours of observations of the vast universe, AI has already been able to detect extraterrestrial radio signals, identifying which planets may harbor life with a stunning hypothesis about the history of life on Earth. Right now, you'll find out how AI is opening up a crack in the mystery of extraterrestrial life, whether we are really the first civilization on Earth. It's no secret that the Drake equation is traditionally used to search for extraterrestrial life. In general, the formula consists of 7 factors that are built on a clear and simple logic that takes into account the rate of formation of planetary systems that are conducive to the development of intelligent life, the share of such systems in the Milky Way, and the average duration of civilization, which can be used to obtain the number of cultures that may exist in the galaxy today. So the simplicity of this formula, if all the members are present, can give us the answer once and for all whether we are alone. But this is where serious difficulties arise. The main drawback of the formula is the absence of all its components at the moment, except for the first one: the rate of formation of stars with conditions suitable for the development of life, which is R. In particular, the value of the period of existence of cultures, L, cannot be calculated due to the probable heterogeneity of the alien behavior, and therefore this factor remains speculative. As long as these gaps exist, establishing a theoretical number for the approximate number of extraterrestrial civilizations will have to be postponed for a long time. But what if there is a way out? Some of the crucial values of the equation FC, Fi, Fl, including L, can be determined without even leaving the planet. The process of the origin of life is incredibly complex. For the development of an intelligent civilization like ours, many conditions must coincide, such as the availability of water in large quantities, heat, climate seasonal changes, the presence of many building and nutrient chemical elements, and so on. Therefore, it is very difficult to search for extraterrestrial life, a mismatch of at least one condition and the planet that can be included in the list of those where a living organism will never appear. Similarly, on Earth, life could have gone through several stages until it reached the level it is now. In other words, intelligent life could have existed long before humans until it disappeared under certain, for example, too difficult climatic conditions. In 2018, two astrophysicists, Adam Frank and Gavin Schmidt, wondered whether it would be possible to detect an industrial civilization using the geological history of the planet. That is, if a developed culture could have existed in the time of the dinosaurs, hundreds of millions of years ago, could there be any evidence of its existence? We're not talking about buildings and statues. They won't be left after a few million years, but about chemical traces, such as carbon accumulation, plastics, radioactive elements, or climatic and ecosystem changes. This thought experiment is called the Silurian hypothesis, based on the eponymous intelligent species that created a civilization before humans in the Doctor Who series. This hypothesis can not only turn the entire history of our planet and question the conditions for the development of life, but it also guides us to an approximate solution to the Drake equation. For example, looking at the extraterrestrial civilizations from the point of view of their impact on the planet can change the approach to future planetary exploration by specifying for scientists what they need to look for. According to NASA, we currently know of 9,820 exoplanets that are candidates for supporting life. Observation on these planets of nitrogen dioxide or chlorofluorocarbons as products of an industrial process may already indicate the existence of an advanced civilization in the past. And the best part is that we can find this trace right now, as this compound can be detected by observing light falling on distant exoplanets, along with various combinations of methane and oxygen in the atmosphere, indicating at least the presence of simple life. Such traces as they relate to technological progress are called technosignatures, created by the hands of civilization. Unlike various biosignatures, which do not guarantee the presence of life, technosignatures cannot be confused with natural processes, so focusing scientists' attention on them can open up the secret world of extraterrestrial civilizations for us much faster and more accurately. Typically, scientists look for technosignatures that match our own technological footprint in outer space. However, according to Adam Frank, aliens are not magic, because their hypothetical civilizations and scientific discoveries are also based on chemical and physical principles known to us. For example, back in the 1960s, SETI scientists came up with the idea of looking for unnatural radio signals in addition to usual biosignatures and pollutants, which remains the most common type of search and still unsuccessful communication with unknown invisible civilizations. However, this method has several serious difficulties, the most important of which is radio signals on the Earth itself, which can be reflected from space objects and mistakenly considered attempts by extraterrestrial life to find us. But in addition to radio signals at this stage of our progress, we can detect industrial gases in the atmosphere, unusual thermal patterns, and polluting particles as high-energy neutrinos. But gases in the atmosphere can also be the product of strange geological activity on the planet, such as the trace amounts of industrial propane gas in the atmosphere of Neptune's moon, Triton, which you can learn about, and possible traces of life on our channel. However, high-energy neutrinos are much less common traces. While ordinary neutrinos are the most abundant particles in the world, high-energy neutrinos, which can hypothetically exceed the energy of ordinary neutrinos by 1 billion times, arise only from accelerators of particles of Planckian, extremely tiny scale. that are not yet available to humanity. The detection of such neutrinos would hint at a significant level of progress of an alien civilization, since such a collider would need an energy density that would allow it to withstand extremely strong electromagnetic fields. And such a place is only located near a black hole. Even more seemingly visible traces of the presence of a highly developed culture in outer space are probable astrophysical structures and transportation, but they are not easy to spot. The most well-known megastructure is the Dyson sphere, a hypothetical technology that orbits a star and captures its energy to meet the energy needs of extraterrestrial life. If such a structure were located thousands of light years from Earth, scientists could track it by observing the eclipse of the star around which the sphere orbits. However, the Dyson sphere can easily be confused with the natural phenomenon of old stars fading due to the vast distance. Spacecraft and probes can also be difficult to identify by movement or strange signals, as they can also be confused with ordinary space objects. For example, a very strange cigar-shaped interstellar object, Oumuamua, discovered in 2017, caused a lot of discussion in the astronomical community because it showed no signs of cometary or asteroid activity. There was a version that Oumuamua was an alien probe, but it was still classified as a comet. Therefore, the search for technosignatures is an extremely difficult task that requires years of analysis, observation, and modeling just to roughly estimate what we're seeing. But our development is just as rapid and does not stand still. In the near future, searching for signs of life on thousands of planets simultaneously will become commonplace. Artificial intelligence will help us reach a new level of progress. Recently, AI has begun to gain massive popularity both among ordinary users and in scientific circles. Astronomical research requires dozens of hours of careful analysis and comparison with previous results, even for a single object. The amount of data to observe just 820 stars is 150 terabytes or 480 hours. With the help of machine learning, this demanding process can be significantly accelerated, and according to the University of Toronto researcher Peter Ma, in combination with the next generations of telescopes, AI will help study and observe millions of stars, not just 100. The benefits of AI in quickly working with gigantic amounts of information extend the search for extraterrestrial life. In 2023, under the direction of Peter Ma, an artificial algorithm analyzed 480 hours of data from the Green Bank Telescope in West Virginia and found more than 20,500 signals similar to technosignals. From this number, scientists selected 8 signals, the Technosignatures, while the rest of the array was made up of intercepted terrestrial radio signals. Despite the manual selection of the signals, the scientists did not have to spend almost a month evaluating what the telescope had recorded. Despite the intriguing findings, repeated listening to the signals yielded no results. Nevertheless, even this first success already demonstrates that AI can now be used for data collection, and that in the future, after various trainings, it will be able to bring clearer results. The biggest challenge for SETI, in fact, is not even the huge amount of information, but the difficulty in distinguishing between human and extraterrestrial signals. Although the first model trained by scientists has already made potentially breakthrough discoveries, it is still unable to distinguish between those technosignals on its own. Currently, scientists plan to use this AI model to analyze new information from telescopes and archival data. In addition to searching for radio signals from intelligent life, AI can also look for biosignals and model their patterns to conclude that life exists on the planet. Recently, scientists from Oxford University, led by Dr. Kimberly Warren Rhodes, trained an AI algorithm to classify biosignatures using the Atacama and Altiplano deserts in South America and their aerial images. In the end, the model was able to detect biosignatures in 87.5% of cases. One of the study participants, Freddie Kalatsis, PhD in computer science, believes that further testing of machine learning will be crucial for the future search for for signs of life and building profitable routes for research on Earth analogs, in particular Mars, as well as the intriguing moons of the solar system's gas giants Europa, Enceladus, and Titan. Moreover, the researchers hope that AI will be able to analyze the mechanisms of life development in planetary systems with extreme conditions, such as perpetual cold, given the array of known data on such planets. In particular, AI can help with less interesting but necessary work to advance what we know about space. AI is able to systemize all the knowledge gained from observations of thousands of space objects. AI can simultaneously examine several factors about a single object, such as its surface composition, terrain features, and other objects that somehow affect the focus of the analysis, presenting scientists with a complete picture of the object of study that would take months of hard work. The imperfections of AI are rapidly decreasing due to constant and varied training, confidently revealing its great potential for thoroughly exploring the entire visible universe and most importantly increasing the likelihood of finding extraterrestrial life. But it also has a downside. AI always has an answer. As strange as it may sound, AI is much faster than humans at seeing patterns and analyzing huge amounts of information. Without the special perception and manner of human work, and based only on its training material, the algorithm can give an answer that astronomers simply will not understand and will not be able to see the possible error. For example, astronomer Ingo Waldman trained an AI called Robert to distinguish between water that may look different in the atmospheres of other planets. But it is not a fact that Robert understood what causes the changes in the molecular composition and pattern of water. Therefore, AI will need to be very meticulously tuned, but its time will come. AI will also be able to not only confirm traces of extraterrestrial life, since the search for technosignatures can be simplified by the ability of AI to analyze data sets through the known history of our planet, it may be a little easier for machine learning to find signs of a pre-human civilization that hypothetically existed on Earth hundreds of millions of years ago. Let's return to the Silurian theory. Although it doesn't yet give any rough ideas of how pre-human society could have developed, we can already make some assumptions. For example, a certain type of intelligent mammal could have appeared 60 million years ago. Its civilization could have existed for only 100,000 years and disappeared due to some cataclysmic event, returning intelligent life to the embryonic stage. However, it is impossible to provide any evidence for this idea. Millions of years for a civilization that is probably not as advanced as ours is absolute oblivion. Even if there are fossils from that period, they could have changed dramatically under the influence of the environment. So according to the Silurian hypothesis, we can find evidence of an ancient civilization based on what people would have left behind. AI will be able to help with this. Machine learning will be able to distinguish a tiny accumulation of industrial waste of a considerable age better than humans, while modeling the approximate path of distribution of these ancient elements. 56 million years ago, the Earth experienced the so-called Paleocene-Eocene thermal maximum, which resulted in 15-degree Fahrenheit rise in global temperatures, with temperatures reaching 70 degrees Fahrenheit at the poles. Scientists also noticed an increase in the ratio of carbon to oxygen in the atmosphere during this period. Perhaps one of the reasons for this was the industrial period of the previous civilization. On the other hand, the emissions could be just a consequence of periodic changes in the temperature background. According to Adam Frank, the RETM did not have a dramatic enough change in the composition of the atmosphere through carbon emissions compared to the industrial era now, so it could have been caused in part by natural processes. However, it is possible that such activities of the previous civilization could have been short-lived. That is, its impact on the Earth was there, but due to its insignificance, it will not be easy to confirm it. On the other hand, a hypothetical pre-human culture, according to a study by the University of Rochester led by Frank and Schmidt, left no traces of pollution like fossil fuels or plastics. Although it is not known whether such technosignatures are common, at least the fuel footprint could be more noticeable for a civilization with a hypothetically long history. This fact makes leading scientists doubt the validity of their own hypothesis. However, the absence of evidence is not proof of absence, says University of Pennsylvania astronomer Jason Wright in response to the Silurian hypothesis. The latest research into the geological history of the ancient Earth using AI may in the near future finally resolve the question of whether we are the first industrialized species on the planet. In particular, even if the hypothesis is not confirmed, it will help scientists find some necessary elements of the Drake equation, and perhaps one day, an inconspicuous trace of carbon on a distant exoplanet will solve the most intriguing question of mankind. No matter how much humanity tries to get closer to the answer to every mystery, the universe will always keep its secrets to itself. Life is the same secret of the infinite universe, which will take hundreds of years for humanity to conquer. The new era of machine learning opens the way for us to solve so many questions about our world, but even with its help, humanity will never be able to get every answer. The age and spatial scales on which the cosmos exist will not be surpassed even by artificial intelligence. However, despite the inaccessibility of full understanding, the universe is still amenable to study and understanding, as curiosity alone drives our progress. For centuries, we have looked to the heavens fascinated by the possibility of life beyond Earth. But what if our search is limited not by the technology we possess, but by the assumptions we make about life itself? What if the key to unlocking this cosmic mystery is hidden in plain sight, in a substance so common but so overlooked? Imagine a world where rivers flow not with water, but with pungent-smelling liquid. A place where the building blocks of life are not carbon molecules floating in water, but complex structures thriving in a sea of ammonia. It sounds like science fiction, but scientists are taking the concept of the existence of ammonia-based life forms more and more seriously. Ever since telescopes reached the stars, humanity has been consumed with the search for life beyond Earth. We've sent rovers to Mars, probes to Venus, and even peered into the icy oceans of Jupiter's satellite Europa. But all these efforts have been guided by a single assumption. Life, wherever it exists, must be something like us, carbon-based and dependent on water. This is where the concept of the Goldilocks zone comes into play. This is a neither too hot nor too cold region around a star where conditions are just right for liquid water to exist. For decades, this zone has been the center of our extraterrestrial search, the celestial point where we believe life is most likely to thrive. From the Viking landing modules on Mars to the Voyager probes traveling beyond our solar system, the hunt for extraterrestrial life has been a hunt for Earth-like conditions. We look for planets with atmospheres similar to our own, signs of water or ice, and even certain gases such as methane and oxygen that might indicate biological activity. But what if this geocentric approach has narrowed our vision? What if, in our search for a mirror of our world, we've overlooked vast expanses where life might exist, but in forms radically different from our own? It's a humbling thought that challenges the very structure of astrobiology. After all, if life can exist without water, then the Goldilocks zone is not the only area in the cosmic real estate market where life can settle. And that brings us to ammonia, a molecule that has long been relegated to the background but is now taking center stage in a potentially game-changing way in our search for life beyond Earth. Did you know that ammonia, a compound you might associate with cleaning products, has a lower freezing point than water, enabling life in an extremely cold condition? Or that ammonia can dissolve a wide range of organic compounds, potentially serving as a medium for various types of biochemical processes? When we think of life, we often envision Earth's blue-green tapestry, forests teeming with wildlife, and oceans filled with a multitude of marine life. But what if there are shades in the palette of life that we haven't even realized? What if beyond the azure oceans and emerald forests there are worlds where life thrives in a golden sea of liquid ammonia? So, venturing beyond the familiar territories of carbon and water, we encounter a molecule that has long been in the shadow of astrobiology: ammonia. This humble molecule, composed of just one nitrogen atom and 3 hydrogen atoms, may hold the key to a life form quite different from our geocentric definitions. At first glance, ammonia seems an unlikely candidate for life support. After all, we're used to thinking of it as a caustic gas, a household cleaner, or an industrial chemical. But when we delve deeper into its chemical properties, a different picture emerges. Like water, ammonia is a polar molecule capable of dissolving a wide range of substances. It can act as a solvent, facilitating complex biochemical reactions, just as water does on Earth. However, ammonia operates under different rules. It has a lower boiling point and a lower freezing point than water. This means that life based on ammonia will exist at temperatures much lower than any earthly organism can tolerate. Imagine a world where the average temperature is well below freezing, but life thrives in oceans of liquid ammonia. Such a world would not only have a different biochemistry, but also different color palette. The sky may have shades of orange and red, and the seas may shimmer with hues of gold or bronze. Very different from the blue and green landscapes we associate with habitability. And just as there is a water cycle on Earth, an ammonia-based world will have its ammonia cycle, complete with ammonia clouds, ammonia rain, and perhaps even ammonia snow. This active cycle would be essential for any potential life forms, providing a dynamic environment for development. If life can exist in Earth's extreme environments, from acidic lakes to deep-sea hydrothermal vents, why not in the ammonia-rich landscape of distant exoplanets? This possibility has the potential to rewrite textbooks and push the boundaries of life as we know it. As we delve deeper into the realm of alternative biochemistry, it's critical to distinguish between 2 key components of life: carbon and water. While both are essential for life on Earth, their roles are distinct, and understanding this difference is crucial when we consider the possibilities of ammonia-based life. First, let's talk about carbon. Carbon is the basis of all known life forms, a versatile element capable of forming complex, stable structures such as proteins, lipids, and DNA. Its ability to form 4 bonds makes it uniquely suited to create the complex molecules that are the building blocks of life. Now let us consider water. Water acts as the stage on which the drama of life unfolds. It is a solvent that facilitates biochemical reactions, allowing molecules to meet, interact, and transform. In essence, if carbon is the actor, water is the theater itself. So what happens if we replace one of these key players? Replacing carbon would mean rethinking the very building blocks of life, a feat that seems almost insurmountable given carbon's unique properties. But what happens if we replace water with ammonia? That's a different story. Ammonia can also act as a solvent, albeit in a colder temperature range, offering an alternative step in the biochemistry of life. As with water, the polarity of ammonia allows it to dissolve various substances, making it an acceptable alternative for facilitating biochemical reactions. However, because of the lower temperatures, reactions are likely to be slower, potentially leading to life forms with a slower metabolic rate. In an ammonia-based world, cells may have membranes composed of lipids stable in ammonia and enzymes that catalyze reactions in this alternative solvent. The genetic material may still be similar to DNA or RNA, but adapted to an ammonia-rich environment. So when we ponder the possibilities of life beyond Earth, the question is not only where to look, but what to look for. Let's delve into the biochemistry of an ammonia-based life form. In such an organism, the role of water as a solvent would be replaced by ammonia. What about the biochemical reactions themselves? Can the enzymes and proteins that facilitate life processes in aquatic organisms adapt to an ammonia-rich environment? The answer is staggeringly possible. Enzymes, biological catalysts, may have evolved to function at lower temperatures and in the unique chemical environment provided by ammonia. These enzymes may be composed of amino acids stable in ammonia, allowing metabolic processes to occur, albeit at a slower rate due to the colder conditions. But what would these life forms look like? In an ammonia-based world, we might find organisms with biochemistry and physiology radically different from our own. Imagine creatures with flexible, elastic skeletons adapted to lower gravity and lower temperatures, or plants that use a different pigment for photosynthesis that absorb and uses light more efficiently. For example, a pigment that absorbs blue or violet light may be more efficient if a planet orbits a star that emits light predominantly in those wavelengths. In designing future space missions, these considerations could be critical. Instruments capable of detecting not only water and oxygen, but also ammonia and other biosignatures would expand our search parameters and allow us to explore these exotic possibilities. The implications of ammonia-based life go far beyond scientific curiosity. They could fundamentally alter our approach to the search for extraterrestrial life by changing the strategies and technologies we use in this great cosmic quest. So far, the parameters of our search have been strongly influenced by our geocentric perspective. We've aimed our telescopes and sent probes to places where we expect to find Earth-like conditions. But if ammonia-based life is possible, then our search field expands exponentially. This means rethinking mission objectives and scientific instruments. Future space probes may have to carry detectors sensitive to ammonia and other non-aqueous solvents. Spectrometers may have to be calibrated to look for unique spectral characteristics of ammonia-based biomolecules. Imagine a new generation of Mars rovers designed to probe the icy satellites of Jupiter and Saturn, not only for water, but for pockets of liquid ammonia. Or orbiters equipped with advanced sensors that can analyze the atmospheres of exoplanets in search of chemical imbalances that might indicate ammonia-based biological activity. The discovery of even ammonia-based microbial life would be a revolutionary event that would leave a lasting impression on the world and change our philosophical and ethical foundations. How would such a discovery affect our understanding of the uniqueness and commonality of life in the universe? What ethical considerations might arise from interacting with or studying these alternative life forms? Education will also transform. Future biology textbooks may include chapters on alternative biochemistry, and astrobiology may become a standard part of educational programs, inspiring a new generation of scientists to think beyond Earth's limits. As we stand on the threshold of this new frontier, the implications of recognizing ammonia as a potential cornerstone of life are enormous. It broadens our horizons, challenges our assumptions, and opens up a universe full of possibilities. Possibilities that may start with a simple molecule, but lead us to worlds beyond our wildest imagination. The observable universe spans 93 billion light-years, a distance beyond our comprehension. In this cosmic space are more than 2 trillion galaxies, each teeming with billions of stars. The scale of the universe is a marvel, but it is not just its size that fascinates us, it is its complexity. The cosmic web, a network of galaxies and dark matter, forms a structure that resembles a vast, interconnected network. Now let's travel to a place equally complex and impressive, the human brain. Composed of some 86 billion neurons, each neuron in the brain is connected to thousands of other neurons, forming a network of unprecedented complexity. The striking similarities between the cosmic web and neural networks are more than a poetic metaphor. It's a scientific curiosity that's led researchers to explore the quantitative similarities between the two systems. Could it be that the universe with its billions of galaxies is reflected in the complex neural networks of our brains? Are we, in some deep sense, a reflection of the cosmos itself? Could it be that the great design of the universe is reflected in the very essence of our being? Do the laws that govern the stars also govern the complex dance of neurons in our minds? These questions, once the domain of philosophers, are now being explored by scientists who are uncovering a connection that may be the key to understanding not only the universe, but also ourselves. Since the dawn of human consciousness, we've been attracted to patterns. The first humans looked up at the night sky, recognizing constellations and tracing the predictable movement of celestial bodies. They observed the cycles of the moon, the changing seasons, and the complex symmetry of leaves and shells. This innate ability to find patterns in nature is not just curiosity. It's a fundamental aspect of our intelligence, the way we understand the world around us. As we evolved, our understanding of patterns changed. We began to realize that these patterns were not simple coincidences, but were governed by fundamental principles and laws. The ancient Greeks discovered the golden ratio, a mathematic constant found in architecture, art, and even the human body. Mathematicians such as Fibonacci discovered sequences that describe the growth patterns of plants and the spiral motion of galaxies. Natural patterns are not limited to static shapes and numbers. They are dynamic, unfolding in time and space. The branching of a tree, the winding course of a river, the swirling of clouds. Everything is subject to mathematical patterns and fractal geometry. These patterns are self-similar. That is, they look the same at any scale, whether you're looking at a single leaf or an entire forest. In the modern age, our search for patterns has led to revolutionary discoveries. The double helical structure of DNA, the strange world of quantum physics, and the butterfly effect and chaos theory all reveal a universe governed by patterns and laws. These discoveries have not only expanded our understanding of the universe, but have also shaped our technology, medicine, and philosophy. But what drives this relentless search for patterns? Is it simply a survival tool, or does it hint at a deeper connection between us and the cosmos? Could our ability to recognize patterns be a reflection of the inner order of the universe, a cosmic signature imprinted in our very being? In a field of scientific research where the mysteries of the cosmos meet the riddles of the human mind, the research of Franco Vazza and Alberto Folletti serve as a beacon of innovation. Their pioneering work has opened new doors in our understanding of the universe and neural networks, revealing striking similarities that challenge our very perception of reality. At the heart of their research is a question that's intrigued scientists and philosophers alike. Is there a connection between the structure of the universe and the neural networks in our brains? Vazza and Folletti have plunged headlong into exploring this question using cutting-edge technology and mathematical models. Their approach was quite quantitative and focused on the distribution of matter in the cosmic web and the connections between brain neurons. By analyzing large data sets and applying advanced algorithms, they found that the structure of the universe and neural networks obey a similar pattern known as degree distribution. A staggered distribution is a mathematical relationship in which a small number of nodes have many links and most have only a few links. This pattern is found in a variety of natural phenomena, from the internet to social networks. Vazza and Folletti found that the same pattern exists in both the cosmic web and the neural networks of the brain. The implications of this discovery are profound. It suggests that the universe and the human brain share a common architecture, a universal structure that transcends scale and complexity. This connection is not just a poetic metaphor, but a scientific reality, a cosmic signature that resonates in the very fabric of existence. The innovative research of Franco Vazza and Alberto Folletti has ignited a spark in the scientific community. Their discovery of structural similarities between the universe and neural networks has opened new doors, leading to a lively dialogue among experts. Dr. Alberto Folletti commented, "Our study is just the beginning of a longer story. We have shown quantitative similarities between these two systems in structural terms. The architectures of these complex networks look strikingly similar. Combining the efforts of neurobiology and astrophysics can expand our ability to get more results." The significance of their findings goes beyond mere academic curiosity. From understanding dark energy to the development of artificial intelligence, the potential applications are enormous. Dr. Alberto Folletti also added, "If we can demonstrate the similarities between a network such as a neural network and the structure of the universe, we may be able to gain more detailed information about the universe and galaxies. This merging of analysis tools from two different disciplines may help in accelerating the process of developing artificial intelligence or artificial neural networks." But the study has also sparked reactions outside the scientific community. Some have used the results to justify creationist theories or New Age viewpoints. Vazza and Folletti clearly emphasized that their work is based on scientific research and has nothing to do with creationist theories or metaphysics. The future of this research is filled with hope and curiosity. Both researchers express a desire to continue exploring this area by looking deeper into the comparison of these two complex systems. They believe that these results need to be analyzed with more sophisticated tools and that the next steps involve moving to a higher level of complexity comparison. As we delve into the mysteries of the mind and the cosmos, we enter a paradox that has both fascinated and puzzled thinkers for generations. In the vast expanse of the universe, where time and space stretch beyond comprehension, lies a paradox that has baffled philosophers and scientists alike: the paradox of Boltzmann's brain. This paradox is named after 19th century physicist Ludwig Boltzmann, and it delves into the very nature of reality and our understanding of consciousness. Boltzmann's original idea was rooted in statistical mechanics, which studied the probability of random fluctuations in a system. Imagine a universe filled with chaos where particles are in constant motion. In this chaos, there's negligible chance that the particles could randomly line up and form a self-conscious brain. This brain, existing for a fleeting moment, would have thoughts, memories, and perceptions of reality, all without a body or a world to live in. The paradox arises when we take into account the vastness of the universe and an infinite amount of time. Given enough time, the random formation of such a brain becomes not just possible, but inevitable. This leads to the unsettling conclusion that it's more likely for a solitary, self-aware brain to exist in the void than for our entire observed universe to have evolved it as it has. The implications of the Boltzman brain paradox are profound and disturbing. If the existence of such a brain is more likely than the existence of our universe, what does this say about our reality? Are our perceptions and experiences merely illusions? Are we too just momentary fluctuations of cosmic chaos? The paradox has sparked debate and reflection among philosophers, scientists, and thinkers. Some see it as a challenge to our understanding of probability and the nature of existence. Others see it as a metaphorical exploration of solipsism, the philosophical idea that only the mind of man necessarily exists. From Boltzmann's enigmatic brain paradox, we venture further into the uncharted territories of consciousness. The question that has intrigued scientists and philosophers alike is whether the universe itself can be conscious. The idea that the universe may possess consciousness is not new. This concept has been explored in various philosophical traditions and resonated in some scientific theories. Historically, the concept of a conscious universe has been associated with panpsychism, the philosophical view that all things possess consciousness. This idea has been adopted by some Eastern and Western philosophical traditions, suggesting that consciousness is a fundamental aspect of reality. In the realm of science, theories suggesting that the universe may possess consciousness have emerged from the study of quantum mechanics. Some interpretations of quantum theory suggest that consciousness plays a role in the collapse of the wave function, implying that the observer and the observed are interconnected. Cosmologists and neurobiologists have also explored this concept to understand how consciousness might manifest itself on a cosmic scale. Theories such as Integrated Information Theory, or IIT, suggest that systems with a high degree of complexity and integration may possess consciousness. This leads to the tantalizing possibility that the universe, with its complex web of galaxies and cosmic structures, may have a form of consciousness. The idea of a conscious universe is still a subject of debate and research, yet it's firmly planted in the realm of speculation. Although it encourages us to think about our place in the cosmos and the interconnectedness of all things, the idea enters metaphysical territory and should therefore be treated with caution and critical thinking. Having considered speculative ideas of a conscious universe, we turn our attention to a more grounded and scientific theory, the fundamental theory of consciousness of Donald Goffman. Dr. Donald Goffman, a renowned neuroscientist and philosopher, has devoted his life to unraveling the mysteries of consciousness. His groundbreaking theory seeks to explain one of the most mysterious phenomena in existence, the nature of conscious awareness. Goffman's theory is built on the premise that consciousness is not simply a byproduct of complex computations in the brain. Instead, he argues that consciousness is a fundamental aspect of reality akin to space and time. Drawing on quantum mechanics, neurobiology, and philosophy, Goffman's theory explores the interplay between micro and macro levels of existence. He suggests that consciousness arises from the complex interactions of quantum particles within the brain, governed by principles beyond traditional physics. Goffman's work has led to new experiments and collaborations across scientific disciplines. His theory's been tested through rigorous empirical research using advanced technology to explore the depths of consciousness. Although Goffman's theory has received the support and admiration of many in the scientific community, it has not been without controversy. Critics argue that the theory's reliance on quantum mechanics and its bold claims about the nature of reality require further confirmation and study. Nevertheless, Donald Goffman's fundamental theory of consciousness offers a new view of consciousness that bridges science and philosophy. The connections between the universe and neural networks go beyond mere scientific curiosity. They open the door to deep philosophical reflection and have broader implications for our understanding of existence. These connections invite us to see the universe not as a collection of isolated objects, but as an interconnected network of relationships. They inspire new ways of looking at technology, ethics, and our responsibilities as inhabitants of the cosmos. The study of the universe and consciousness has been a central theme of philosophy for millennia. From ancient Greek thinkers to modern philosophers, the quest to understand reality, existence, and our place in the universe has shaped human thinking. Some see the universe as a deterministic machine, while others take a more mystical view. The connections between the universe and the mind only add a new dimension to this age-old debate. The idea of interconnectedness is not just a scientific observation, it is a call to reflection. It invites us to see ourselves as part of a greater whole, realizing the delicate balance of life and the universe. It forces us to think beyond ourselves and consider the impact of our actions on the wider cosmos. The journey ahead promises exciting discoveries. While the connections between the universe and neural networks are fascinating, it's important to approach them with scientific rigor. Misinterpretations and sensationalism can lead to misunderstandings and detract from the true scientific value of these discoveries. So let our curiosity guide us in our explanation of the cosmos, and let our critical thinking help us stay grounded as we continue to explore the uncharted territories of understanding the universe.